I'm Jack Holt, and I have the honor of introducing our speaker today, Dr. Ariel Anbar. Ariel received his bachelor's from Harvard, his master's and PhD from Caltech, where he had to endure distracting office mates who will go unnamed. Worked with Jerry Wasserberg and Yuck Young, and I believe you were Wasserberg's last student, right? Ariel was the person that retired Wasserberg. He's like, I'm done, I can't. Right, see? Yeah. The last success. So then he was an assistant professor and then associate professor at University of Rochester for a while, both earth and environmental sciences and Department of Chemistry. And then since 2004, he's been at ASU, where he became full professor and now is president's professor, Howard Hughes Medical Institute professor in both the School of Earth and Science Exploration and School of Molecular Sciences. Lots of titles, yes. He's been awarded the Donath Medal by GSA. He's a fellow of GSA, a fellow of the Geochemical Society, and also the European Association of Geochemistry. And Ariel is well known for doing a wide variety of really interesting fundamental research on a variety of problems. Also, he's been spearheading a big education program at ASU. He's director of the Center for Education through Exploration, which is doing some really innovative digital learning work. So, but he's not going to tell you about that today. He's going to tell us about redox revolutions from on Earth and beyond. So let's have a warm welcome for Ariel.
Thanks. Is this working? Yeah, it's working. So thanks. Yeah, there were a lot of bottle rockets fired out of office windows. Not ours, though. And you had nothing to do with that. Yeah, there was. So John and I have known each other. Jack, I know him as John. See, I can't do this Jack thing for a long time, so way too long. So I'm pleased to be here and to talk to you about redox revolutions, Earth and beyond. The work I'm going to talk about is, to a large extent, the product of work that I, as well as colleagues and students, have been doing as part of two big projects. The NSF Dynamics of Earth System Oxygenation team at ASU, which I'll talk about just a little bit in a minute. And then I'm also part of the NASA Nexus for Exoplanetary System Science team that's based at ASU. You guys have a Nexus team here as well. And some of the astrobiological thinking from that team will show up in this presentation. But a lot of the work is going to be work that stemmed from this NSF project, Dynamics of Earth System Oxygenation. This was a NSF FESD project. FESD is Frontiers in Earth System Dynamics, project that just ended. We're actually in our second no-cost extension to spend out the last $15,000 that are still left. But this was a 5-year, $5 million project involving 5 institutions and lots of PIs around the topic of trying to understand better the history of oxygen on this planet, and in particular the role that the solid Earth played in the evolution of oxygen in the Earth's atmosphere. So I'm going to give you a flavor of that and showcase a little bit of the work that came out of that project, as well as some of the work that came out of that project done by some of my students, as well as a few other students. So I'm going to be selectively going through the field and the topic. I'm not going to be doing credit to all the workers out there who are doing things related to all this. So I'm just going to apologize in advance if your favorite paper isn't mentioned. I'm telling a story through a particular lens of this project here. In terms of motivation, and maybe I'll just try to give away the punchline here. So I've long been fascinated by the "Are we alone?" question, by the pursuit of other pale blue dots. Oh, look, the battery's dying. That's really useful. Is there another one here? This is mine, so it's my fault the battery's dying. So let's see. There's another one here that I bet has fresh batteries. Yeah, here you go. This thing, this pale blue dot circled by this bright green dot. So I've long been fascinated by the "Are we alone?" question, the search for life on other worlds, informed by our understanding of Earth and Earth history. If we want to look for other pale blue dots, we need to understand this one better. And there's sort of 2 take-home messages I want you to take away. Take-home messages, so you better take them away. That's kind of just straightforward. One of them is one you've probably heard before, which is that if we want to understand, if we want to look for life on other worlds that might be like our own, it behooves us to understand the history of this planet, because what we look at out there, even if it's an exact replica of Earth in some ways, will not necessarily look like Earth does today, and Earth has had a long and varied history. That's a common message. You may have heard that before. What's a slightly less common message is to tell you that we don't understand this thing well enough at a systems level to inform the search for life on other worlds in the way that it needs to be informed if it's going to be efficient and smart. And that's a message that's not so commonly heard, and I hope by the end of the talk you'll understand what I mean by that. So it's this notion that we need to understand the Earth as a system, and that we do not understand the Earth as a system right now in anywhere close to the level that we need, in some very basic and fundamental ways. I'm not talking about sophisticated nuances. I'm going to talk about some very big picture things that we just don't get about this planet, that until we get, we can't really search for life on other worlds, search for pale blue dots in a way that's particularly efficient. So hopefully soon you'll know what that means. Okay, so I've got two. So this is going to be kind of fun. So the theme of this talk is really rooted in what's coming, which I think you guys here know about more than most audiences I might talk to, which is the search for biosignatures, the search for life on other worlds using spectroscopic techniques. Right, using spectroscopic methods to look for gases in the atmospheres of planets during transit observations, in particular, that could be indicative of biological activity. Oxygen looms very large in conversations, planning for this kind of research. This is a beautiful photo. It's like this iconic photo, this nice oxygen bubble emerging from a cyanobacterial mat in the laboratory. So this is, oxygen being produced by biology. So oxygen looms large in our search for life because on Earth we have a dominantly oxygen atmosphere, heavily oxygenated atmosphere because of biology on the planet. And I'm sure you've heard other talks, or you will, or you can look at papers that make the case that with some exceptions, which we can kind of understand and model, to have a heavily oxygenated atmosphere requires life. You can do it photochemically too under certain circumstances, and we can predict and model those, and you can get false positives, and we understand that challenge. But for Earth, certainly an Earth-like planet around a sun-like star, the presence of a 20% oxygen atmosphere is pretty diagnostic of biology, so it's a pretty good biosignature. And it's one that we can detect spectroscopically pretty easily, relatively, compared to other things. So this is the sort of classic, iconic, canonical kind of a comparison. Here's Venus, here's Earth, here's Mars. Here are spectra in the infrared of the atmospheres of these three planets. So Venus, you see this very heavy CO2 feature. It's a 90+% CO2 atmosphere, so you get very strong CO2 absorption. Here's Mars. Even though it's a very thin, wispy atmosphere at 6 millibars, it's still basically the same chemically. It's dominantly CO2. It's just a much lower pressure. And here's Earth. On Earth, CO2 is a much lower proportion of the atmosphere than it is on either Venus or Mars. And you see this strong absorption feature due to ozone, which is a byproduct of oxygen. So this is an example of Earth spectroscopically looking quite distinct from these other two worlds. It looks quite distinct in this particular wavelength region because of this byproduct of oxygen chemistry. And given enough context about the photochemical conditions in the atmosphere, you can make the argument, you can convince yourself that the amount of oxygen you need to make this ozone can only be explained if you have some big source of oxygen at the Earth's surface, which would be biology. All right, so if we saw, knowing the context that we know about Earth, if we saw a spectra like this from an Earth-like planet elsewhere that had the same context, we could make a pretty strong case that there's life on that planet. We could rule out the false positives pretty readily and say, oh, bingo, if we could make this kind of observation. So this is what animates and drives the notion of oxygen as a biosignature. And it's a fine notion. I'm not going to challenge that at all. But I am going to say we need to understand planets much better to make good use of this. So let's look at Earth through time. This is a figure from a review paper in Science by my friend and colleague Tim Lyons, sort of trying to synthesize through time, so from 4 billion years ago to the present, oxygen in the atmosphere in a kind of semi-cartoonish way, or let's be honest, a very cartoonish way, because our knowledge is actually pretty poor, but it's good enough to make some useful cartoons. Pick your favorite unit for oxygen, so you can do atmospheres, or you can do what's done in the biz, which is PAL, which stands for percent of a fraction of present atmospheric level. PAL is present atmospheric level. It's a very arcane unit. So take your pick. Either way, we have this history here where for the first half of Earth history, roughly, oxygen was, we think, the conventional interpretation of the community is that it was at very low levels, vanishingly low. There may have been whiffs of oxygen in the late Archean. We'll talk a lot about that in a few minutes. A big rise in oxygen called the Great Oxidation Event, or GOE in the biz. So if you hear me say GOE, I'm referring to the Great Oxidation Event. And then another long period of time here where we actually have a lot of uncertainty. There's a lot of argument and debate about just how high or low oxygen was, but it was definitely appreciably higher than what came before, but still lower than what came after. What came after is about 500 million years ago, the so-called neoproterozoic, not enough sleep last night, neoproterozoic oxidation event, which led to this sort of 20-ish% oxygen atmosphere that we have now with some variations. So this is the history of oxygen, history of molecular oxygen, O2, in Earth's atmosphere. And if you think about this from an astrobiological perspective, you can do this kind of classification scheme. During this period of time, so Earth had life during all this time. It's pretty hard to argue that we didn't have life on Earth, at least back to 3.5, probably back to 3.8. And I'm going to make the case for you that we probably had photosynthetic life making oxygen during much of this time too. But regardless of that, there was life through most of this time, but it was undetectable through the approach that we're talking about now. During this window of time, there's arguments about an oxygen overshoot here, that maybe we reached as high as 20%. So maybe there's a brief window here where oxygen would have been detectable at sort of modern levels. But then it settled back down into something lower where most likely with the kind of technology we're talking about using, it would have been barely detectable and only became unambiguously detectable in the last 500 million years, which is to say the last 10% of Earth history. So for most of Earth history, we can say with strong confidence there was life on Earth. There was life on Earth making oxygen, but it was not detectable astrobiologically. The strong case for detection would only be in the last 10% of Earth history. So that being the case, we might want to understand what modulates all this, what controls all this. Because we're about to embark on the next generation of big space telescopes. There's people here who know much more about LUVOIR than I do. The next generation space telescope designed specifically to go after biosignatures like oxygen. We're going to spend a lot of money on these telescopes. Observing time is most likely going to be really precious. And we're going to have to pick our shots. We're going to have to decide which planet do you want to focus on. Right? That's going to be the next generation or the generation after that's challenge. Which planets do you want to focus on? And you'd like those bets to be smart bets. It would be unfortunate if we turned out to spend lots and lots of time looking for oxygen in the atmospheres of planets that retrospectively, if we actually understood the planet as a system, we said later on, wow, that was a big waste of time because oxygen would never accumulate on that planet even if it was being pumped out. Right? We'd like to have a systems level understanding. We'd like to be able to, from mass and some basic compositional information, be able to make predictions with some confidence about whether a planet, if it has life that makes oxygen like Earth, if it will actually accumulate in the atmosphere. Right? I'm not asking about the origin of life question or evolution question. Let's stipulate that all planets have life like Earth pumping out oxygen. That's obviously not true, but let's stipulate that that's the case. On which ones will oxygen accumulate in the atmosphere? Can we make predictions about that based on mass and composition, the kind of things we can hope to observe, gross composition, the kind of things we can hope to observe and infer from Earth-based observations? And until we can do that, we're going to be doing kind of this random thing, hoping that we find the ones where oxygen can accumulate. For all we know, Earth is very exceptional. Maybe it's very unusual to be able to have a planet where oxygen can accumulate, even if you have it being produced on the surface. So this is the kind of systems level understanding we'd like to have. So we'd like to understand what modulates oxygen through its history. Can we get some handle on this systems level story? So some questions then emerge as you start thinking about this. So this is photosynthesis. This is the way a geochemist writes the photosynthetic reaction. It horrifies biochemists, right? Because it doesn't actually work like this, but it's stoichiometrically correct, so we'll go with it. So some questions about this. Did biological O2 production significantly predate the Great Oxidation Event? I told you that it did, but how well do we really know that? A lot of the research that we've been doing is around that. And if so, if oxygen was being produced significantly before the Great Oxidation Event, what kept O2 from rising? What modulates O2? And especially what caused the change between a world with almost no O2 before the Great Oxidation Event and a world that had appreciable amounts afterwards? And what are the implications for astrobiology? So this is what I want to go to address in the talk. So we're 15 minutes in. That's pretty good. So, right. So, sorry, I missed my own little prompt here, right? So let's first tackle this one here. Did biological O2 production significantly predate the Great Oxidation Event? I've already told you that I think it does. What I'm going to do here is walk through some of the cool recent evidence of that, which you may not have seen before, and give you a little bit of a simple framework in which to think about this. So in terms of thinking about what causes oxygen to rise or fall in the atmosphere, you want to think very simply, and the simplest way we can think about this that's at least a little sophisticated is to think in terms of a balance between sources and sinks. I say this is a little bit sophisticated, and I belabor this because when I talk about this with people, even with very erudite scientists, the first thing they say is, oh, the great oxidation event, that's when photosynthesis was invented, right? So it's like sinks don't matter, it's just magic. This is when the source was invented. Right? So yeah, that could be true. That's hypothetically possible, but let's at least begin with a framework that says that we're agnostic about that, right? That it's a balance between sources and sinks, and we'll think about this in that kind of framework. So sources versus sinks. So what is the sources story? So there are classic lines of evidence. If you went through a basic classic geology program at some point, or course at some point, you have heard about these kind of arguments, hopefully, because they're the classic ones, and they're perfectly reasonable. And like many things in geoscience, they come in and out of fashion as to what we believe they mean. So we have, in the first half of Earth history, we have copious deposition of banded iron formations, these vast deposits of iron oxide, which classically have been interpreted to tell us two things. One is that the oceans dominantly had very little oxygen, and hence they could accumulate lots of iron, and they could have lots of iron dissolved in them. But also that there had to be small areas, at least, nearshore environments most likely is the classic story, where oxygen was being produced so that that dissolved iron, which was dissolved as iron 2, could oxidize and precipitate out as iron 3 to make these things. Right? So these have classically been interpreted in this kind of bimodal way to tell us we had oceans that were dominantly anoxic, but zones of oxygenation probably due to photosynthetic production of O2 in the Archean. And these rocks, some of the oldest rocks we have actually are arguably banded iron formations. And so you can make the argument, and it's been made classically, that we had anoxic oceans with oxic surface environments to deposit, to create oxidation of iron conditions as far back as we can go in the geologic record. That's a case you can make that's pretty reasonable, actually, classical geological principles. There are other arguments that have been made that are anoxic, and they're perfectly reasonable too, and so it's a debate. It's not definitive. We also find in the geologic record stromatolites, these rock formations that in some cases are inarguably, I would say at this point, the remains of microbial mats that were most likely, that were phototactic, that were using light. And the case can be made pretty reasonably that many of these were microbial mats making oxygen. And then we can argue about how good that evidence is as we go further back in time. There are those who would argue that the oldest stromatolites at 3.5 billion years were making oxygen, and then there are people who argue against that. It's controversial. But you can make the argument, right? So there are classic geological arguments for oxygen being produced pretty early. What I want to expose you to is some non-classical arguments, some of the new stuff. So because this has been argued about, it's worth always generating new lines of evidence. So in particular, I'm going to focus on lines of evidence stemming from the chemistry of molybdenum and its isotopes, as well as thallium. Why molybdenum? How many of you guys have read Hitchhiker's Guide to the Galaxy? Life, the universe, what's the answer to the question of life, the universe, and everything? It's 42. This is element number 42. So of course we're going to focus on molybdenum. What else would you focus on? That's a joke I've been telling for 20 years, and it's still a good joke. It always works. All right. So what's the basic story with molybdenum? Why would we look at molybdenum from a standpoint of paleoredox? So molybdenum in igneous rocks and crustal rocks is bound up in sulfide minerals, pyrites, molybdenites, things like that. And so the geochemistry of molybdenum is such that if oxygen is present, you get molybdenum weathering out of those sulfides. The sulfides oxidize, the molybdenum gets released, goes into the oceans. Molybdenum is quite happy as the molybdate oxyanion and soluble and accumulates in seawater, builds up to high concentrations in seawater. In the modern oceans, molybdenum is the most abundant transition metal. If you want to impress very geeky friends at very geeky cocktail parties, ask them what's the most abundant transition metal of the oceans, and you can tell them it's molybdenum. It's only 100 nanomolar concentration. The oceans are pretty dilute when it comes to transition metals, but it's molybdenum. So in an oxygenated world, molybdenum is mobilized, accumulates in seawater, and then gets removed from seawater in environments that have high concentrations of hydrogen sulfide, so-called euxinic environments. Molybdenum becomes very immobilized in those environments for reasons we could go into and are argued about a little bit, but it happens. And so sediments that accumulate under euxinic water bodies, under sulfidic water bodies, are rich in molybdenum today because the oceans are rich in molybdenum, and the oceans are rich in molybdenum because it weathers out of the sulfides. So you get this very nice oxidative story. If you don't have oxygen around, or anything that is strongly oxidizing, the molybdenum is going to stay bound up in the sulfides in the continents, doesn't accumulate in the oceans, and doesn't end up in those sulfide-rich sediments. So it's like a switch. And in fact, in some of the older literature, literally molybdenum was talked about as this redox switch, that you could say something about ancient ocean molybdenum and hence oxygen based on the abundance of molybdenum in sediments deposited in these kind of environments. The kind of sediments we're talking about are black shales. So here's a beautiful black shale from 2.5 billion years ago. We're going to talk a lot about some of the chemistry from these particular rocks. So the game that one can play is to look for black shales through time. So sediments deposited under sulfide-rich conditions, measure the molybdenum concentration, as well as some other things that give us some important context, and say something about the molybdenum concentrations of ancient oceans, and from that infer something about the oxygen abundance in ancient environments. And that game was developed over the past 15, 20 years, particularly by my friend Tim Lyons and a former student of his, Clint Scott, as well as me and others working with them. And you get these kind of records. So here's 3 billion years ago to today. Here's molybdenum in black shales. This is a big data compilation. And you see here some variation through time, and it's variation that kind of mirrors this 3-stage oxygen story that I showed you before. Very low molybdenum in these Archean rocks, sort of intermediate here in these Proterozoic rocks, and then you get to the Phanerozoic, and molybdenum concentrations shoot way up. The upper limit shoots way up. And the interpretation of this is, well, that what you're seeing here is an environment with almost no oxygen around, some oxygen around, lots of oxygen around. And so molybdenum mobilization and accumulation in the oceans and in these sediments tracks that. And we're actually pretty happy with that story. I mean, we could go into it in detail. It's been tested in various ways, and it's a pretty good story. So I'm not going to challenge that at all here. So one thing that we did a number of years ago is to go back in time here to 2.5 billion years ago. So this is just before the Great Oxidation Event, 100 to 200 million years before, depending on how you count. And look to see, let's look in real detail. Notice there's not a whole lot of data here. Let's take one particular suite of rocks deposited over 10 to 15 million years and look in detail and see, is there any story here that we've missed in our gallivanting through the geologic record at low resolution. So this was a story that we told back in 2007 originally, where we looked at black shales at this particular period of time, at 2.5 billion years ago, and found elevated molybdenum concentrations in this particular shale unit here. That it's not just the molybdenum concentration as well as other things that led to this notion that, so we see elevated molybdenum in these sediments that we interpreted then as evidence of trace oxygen in the environment before the Great Oxidation Event. We called it a whiff of oxygen. This has now kind of become a canonical thing, the whiff. People talk about the whiff. This is the whiff. You probably haven't heard about the whiff. It's not that common knowledge, but in the biz, right, we talk about the whiff of oxygen. So that's this. So that's all that's fundamentally based on this molybdenum enrichment that is interpreted through the logic that I just gave you. And this is, as I said, 100 to 200 million years before the Great Oxidation Event. Since then, a whole lot of other evidence have been developed, of which this is just some, a whole lot of other proxies, molybdenum isotopes, iron isotopes, uranium isotopes, nitrogen isotopes, selenium isotopes, rhenium isotopes we now are working on. There's a whole lot of stuff that's been done that all shows interesting kicks here, that each of which, you can quibble and you can come up with other interpretations, but you take the totality of it and it's hard, parsimoniously, it's hard to get away from a redox change in the environment as the simplest explanation, and oxygen is the simplest way to perturb the redox condition of the environment. And so we think it's a pretty robust argument at this point that at 2.5 billion years ago we had one of possibly many events where there was transient oxygen in the environment, a whiff of oxygen in the environment. That's great. So that leads to some questions, some sub-questions here. How widespread was this oxygenation? What was the actual atmospheric PO2? How much oxygen was there in the atmosphere? And how far back does such evidence go? And just to cruise through this, we'll try to do it justice, but in a rapid pace. We'll try to go through each of those questions a little bit with some of the most recent stuff we've been doing. So you can make this interesting prediction that if you're interested in how extensive the oxygenation might have been in the oceans, you can start to ask yourself, well, might there have been fully oxygenated water columns where oxygen was not just present at the surface, but all the way down to the seafloor, at least in shallow water environments and in continental margin type environments, near shore environments. If there was oxygen down to the sediment floor, then you can bury manganese oxides. To bury manganese oxides, you need to actually have O2 penetrate the sediment-water interface. And so we became interested, and others have become interested in, can we diagnose between these two conditions? Widespread oxygen penetration of the sediment-water interface versus not, which has an effect on manganese. Are there ways to diagnose this? And the manganese is interesting because, as it turns out, some of our favorite isotope systems turn out to be fractionated when the element adsorbs onto manganese oxides. So in particular, this is Chad Ostrander, a student finishing up his PhD now, who did this very nice work. So under oxic conditions, as it turns out, I'm just giving, I don't want to turn this into isotope talks. I'm giving this to you in like very high-level cartoon fashion. Under oxic conditions where you deposit manganese oxides and bury them below the sediment-water interface, it turns out that light molybdenum isotopes preferentially go into the manganese oxides, and heavy thallium isotopes preferentially go into the manganese oxides, leaving the overlying seawater light in thallium and heavy in molybdenum. And whatever the prevailing seawater, thallium, and molybdenum are, that gets sampled in local environments that happen to be sulfidic. Like today, the modern Black Sea is an example of such an environment. Any place that you have black shales deposited that meet certain criteria are environments where you had sulfide in the water column. And we can find such environments throughout geologic time. So we can go to black shales, look at the thallium and molybdenum isotopes in those black shales, and from that infer what the thallium and molybdenum isotope compositions were in the ambient seawater, and infer from that whether or not manganese oxides are being deposited. So there's a game we can play here. So Chad had the idea, working, and Jeremy Owens, who was a postdoc at Woods Hole he was working with at the time, and Sune Nielsen's group, they collectively came up with this idea that there should be, because of this difference in fractionation direction, that there should be an anti-correlation between thallium and molybdenum isotopes if manganese oxides are the story in causing shifts in these isotope systems. So they had this. They actually made a prediction that then we could actually go and test, and as it turns out, it actually works. They predicted that if we go into black shales through time, in periods where there might have been pervasive oxygenation, we should see, where manganese oxides might have been buried, we should see an anti-correlation of these two isotope systems. And so then Chad had the idea, well, hey, this Mount McRae shale from 2.5 billion years ago where there's all this whiff of oxygen evidence, let's go look there. So he was a student working with me, had access to these samples, and so went and did it. And so this is what we find here. So this is in this same black shale unit we've showed where we have the other whiff data. So what you see here is you go up through this section, you see thallium and molybdenum isotopes fractionated such that the thallium is light, the molybdenum is heavy. Then you go up into this middle section and they come back together and then they go back apart. They're like moving in opposite directions. This is actually statistically robust. On a cross plot, it looks kind of ratty, but you can do very statistical tests and convince you there really is an anti-correlation of the thallium and molybdenum here. And so this is the kind of evidence that we're now looking at, using multiple proxies, piecing them together to try to say something about the ancient environments. And what we think this tells us is that there was, as it says here, fully oxygenated water columns over continental shelves before the Great Oxidation Event. Not everywhere, not all the time, but the oxygen wasn't just trace amounts here and there. There was significant amounts in the water column at certain places at certain times, enough to leave some pretty powerful fingerprints. So the picture that emerges is that during these whiff intervals, right, we probably had nearshore environments that look kind of like this, with oxygenated surface waters depositing manganese oxides and doing their thallium and molybdenum isotope trick, on top of bulk oceans that were dominantly anoxic, so things like iron could accumulate in the water, with localized environments today where you have oxygen minimum zones. Back then you probably had sulfide maximum zones where you would make black shales or the sedimentary precursors to black shales. So this is the kind of world that we're now imagining, which is actually the same world I grew up with when I was an undergrad in the 1980s learning classical Precambrian geology, because this is the world that Preston Cloud and others painted from banded iron formations and stromatolites. And it's a world that kind of receded based on various other arguments, but now I think we're bringing it back and saying, no, this is probably what the Archean was like. There was oxygen being produced, and it was accumulating in non-trivial amounts. How much oxygen was in that atmosphere? So folks have tried to reconstruct this from sulfur isotopes. Zhenming Liu was a student in Roger Summon's group at MIT who did mass independent sulfur work as part of this FESD project. And so based on his sulfur work and some associated modeling, came up with these sort of constraints on atmospheric oxygen, with the kind of broad still. Well, this is later, but earlier on, right? You have this kind of 10 to the minus 8 or so bars of oxygen, so very, very trace. So we asked the question, okay, so we're seeing molybdenum in these rocks, and it's the result of oxidative weathering. Can we come up with an independent way of getting at oxygen levels from the molybdenum story? Because if you think about it, I've got oxidative weathering here that's bringing molybdenum into the water, which then gets sampled in these sulfide-rich areas. So this is what we're measuring, the rocks deposited here. But the rocks deposited here have molybdenum or not because of weathering that happened here. So what do we know about the rate of weathering as a function of oxygen? And can we build models based on knowing that rate that can relate PO2 in the atmosphere to molybdenum concentration in the sediments? The key thing to understand is what's the rate of oxidative weathering. Turns out that no one had done the experiments at such low levels of O2 as might be necessary, and nobody knew if you could extrapolate from high levels of O2 to low levels of O2. So Alicia Johnson, another graduate student who's part of this FESD project, who's also now finishing up, both Chad and Alicia are on the job markets if you're looking for good geochemists. I got people who are awesome. So she did these very difficult experiments working with Don Canfield's group and some others who had developed these sensors that allow us to actually measure oxygen concentrations down at the ppm and lower level reasonably well in these kind of experiments. So she did these sulfide weathering experiments. We won't talk about this in detail. This is just a typical kind of a compilation of some of this experimental data. Here she's looking at the rate of breakdown of molybdenite, molybdenum sulfide, versus atmospheric O2. So we have data here at sort of 10 to the minus 5, 10 to the minus 4, 10 to the minus 3 PAL. So this is fraction of present atmospheric level, so multiplied by 10. So this is down to the ppm level of O2. And these data didn't exist before. Everyone was extrapolating from way over here and hoping that behavior was linear. Turns out behavior is linear, so that's good. And so then you can build models to come up with curves like this. This is oxygen here again on the x-axis now. So as a function of oxygen, using those kind of reaction rate data, we can model what the river flux of molybdenum would have been, what the flux of molybdenum down the rivers would have been. And we can build mass balance models of the ocean and ask ourselves, what's the minimum flux that we need to satisfy the molybdenum isotope and molybdenum concentration mass balance? That's here, and that crosses that crosses this curve at about a ppm. And so the argument that we seem to be coming with from the molybdenum is that the concentration of oxygen in the atmosphere was probably as little as a ppm of oxygen would be enough to explain all the molybdenum story that we see. Right, so when we talk about a whiff of oxygen, what are we talking about? We're talking about as little as a part per million oxygen in the atmosphere. That's all you need to start oxidizing sulfides fast enough to cause the kind of molybdenum enrichments that we see in the sediments. So the whiffs really are whiffs. It's not like you could walk around breathing. You wouldn't notice it because it's way below anything that animals can make use of. So how far back can we find? So we have good reason to think that there was oxygen being produced in the environment and accumulating in the ocean environment before the Great Oxidation Event. In the atmosphere, it was probably still quite low, very trace, even though it was significant in the oceans. That makes sense because if it's photosynthetic organisms in the oceans pumping out the oxygen, that's where the concentration should be higher. And then we can ask ourselves, well, can we develop the kind of concentration and isotope data that I've talked about earlier in the geologic record, and folks have done that. The oldest is Noah Planavsky's work, which appeared in, I think it was in Nature in 2014. We won't go through the details of this argument, but it's a molybdenum isotope argument that argues for manganese oxide deposition as old as 3 billion years ago, that based just on molybdenum isotopes and some inferences. So you can make a case pretty strongly based on these trace metal arguments that we had oxygen production and accumulation in the ocean, most likely by photosynthetic bacteria, as far back as 3.0. And it's not like before that we have evidence that wasn't happening. It's just we don't have good rocks where we can test one way or the other, right? So I'm looking at Batul here for a second because I'm realizing that I actually made a point of not having anything about molecular evidence here of when oxygenic photosynthesis existed, because I would butcher it and not do it justice. But you have somebody here who's like a world expert in talking to you about what the molecular arguments are. And the molecular evolution arguments also allow for early oxygenic photosynthesis. There's nothing out there that says it couldn't have been the case, and there's plenty of evidence that it probably was there. Okay, so what kept O2 from rising? So I hope I've convinced you by now that there was most likely oxygen production, there was most likely oxygen accumulation at low levels, at not trivial levels of the oceans, at very low levels in the atmosphere. So what kept it from taking off? Right, so the naive thing you might read in an introductory biology textbook, that the great oxidation event, the takeover of oxygen in the atmosphere, takeover of the atmosphere by oxygen is due to the origin of photosynthesis. That's a necessary condition, but it's not sufficient. It's not that simple. Oxygen was probably being produced long before that, and something kept it from rising. So what is that something? Well, we could come up with all sorts of ideas. What I want to expose you to is a particular set of ideas that we think are pretty powerful emerging from this NSF-FESD project. So the story focuses on sinks, not on sources. We could make some interesting hypotheses based on sources that we could talk about later, but I want to focus on the sink side of this now. So what are the sinks for oxygen on the long term, on geologic timescales? So oxygen is being produced biologically, and on geologic timescales, that production is thought about not in terms of the biological production, but actually about the burial of organic carbon, because when you make oxygen, you also make organic carbon, and the only way to actually leave oxygen behind in the atmosphere biologically is to take some of that organic carbon and bury it so it doesn't reoxidize, that same year or a decade later. So the biological source of oxygen on geologic timescales is thought about in terms of burial of organic carbon. If that seems confusing, I'm sorry, we could spend some time on that later. Just take it as a given. Everything we've been talking about so far about photosynthetic oxygen is this arrow here. There's also some production of oxygen from escape of hydrogen to space. We haven't talked about that here. It's important. It's not clear that it dominates the story, but it's something you have to consider in these models. So those sources of oxygen are balanced against sinks. The sinks that matter, geologically speaking, are all geological. It's weathering, it's a reaction of oxygen with various reduced materials. It's continental weathering, it's reaction with submarine volcanic gases, it's submarine weathering, it's reaction with volcanic gases, subaerially, metamorphic gases. Right? So we can take our little equation and expand it out a little bit here. So here's our source terms, our biological net production and our hydrogen escape production of oxygen. And then here are sinks, which are volcanic, metamorphic, and weathering fluxes. Oops. So there are a number of papers that have come out, and this is just a subset of them, over the last 15 years or so, looking at the sink side of things, trying to make the case from various directions that the solid Earth's evolution really played an important role, because the solid Earth's evolution is what affects those sinks, continental weathering, volcanic gases, metamorphic gases. Those things are all fundamentally solid Earth geological byproducts. The classic idea, though, which we then decided to revisit, was the notion that perhaps the redox state of the Earth's mantle actually is not constant, but evolves, or at least of the source region for volcanic gases evolves over time. So this is an idea that was laid out by Dick Holland, who was my undergraduate mentor and was one of the pioneers in doing research around the Great Oxidation Event. This was one of his later papers. So here he was trying to reanalyze an old idea that he and others had about volcanic gases and black smokers and the effect of reductants from the Earth's interior on the Great Oxidation Event. And he has these couple nice statements here. So it is shown that the required increase in the FO2, FO2 is the way solid Earth folks, who there are some here in the room, I think, petrologists in particular, think about oxygen fugacity. So it is shown that it's analogous in a sense to partial pressure. That's good enough for present purposes to think about it that way, except it's very low levels. It is shown that the required increase in the oxygen fugacity of volcanic gases was less than 0.5 log units. Variation of this magnitude is not strictly ruled out by existing data because the resolution of the existing data is only about 1 log unit. So just to put that into pictorial terms, what have we been confident of through 2011, a little bit beyond, about Mantle Redox Evolution? Well, here's time. This is kind of a weird axis. It's a semi-log kind of a scale here. So that's why things are stretched out here early. This is early, this is today. So the numbers are actually backwards from the way I've been showing it to you before. But this is today. This is 4.5 billion years ago. Here's oxygen fugacity relative to iron wustite buffer. And so we know, I mean, nobody argues that there wasn't early mantle redox evolution, because when you form the core of the planet, right, you're taking all this iron and you're putting it in the middle, right? That iron is iron metal, so it's very chemically reduced. And you leave behind a mantle that is more oxidized than it was before. So there's a big early mantle oxidation event. But then beyond that, there have been attempts to try to get at mantle redox evolution, but they all had fairly large error bars. These boxes actually denote the error bars. And remember what Dick argued is that you only need about 0.5 log units, only 0.5 on this scale, to actually explain the great oxidation event. And that's within the size of these the height of these boxes, right? So the data simply have not been good enough to say whether there's been any secular change in the redox state of the mantle since this very early core formation induced oxidation. So one of the, I like to think one of the more important things we did in this FESD project is Willie Nicholas, working with Igor Puchtel at University of Maryland, calibrated a novel approach to getting at this question, looking at partitioning of vanadium between olivine and melt by looking at Komatiites. So you're looking at bulk rock vanadium versus what's in the olivines. That partitioning turns out to be sensitive to oxygen fugacity. So this is a calibration curve of oxygen fugacity relative to nickel oxide, and partitioning of vanadium between olivine and liquid. You get these nice calibration curves that Willie developed. And then he went to ancient Komatiites and looked through time to see, okay, given that calibration, what can we say? So here's time, 4 billion years ago to the present. Here's oxygen fugacity. And if you look at Komatiites through time, what Willie saw was has found is this very interesting trend, which is, there's enough data here now that it's statistically reasonably robust that it looks like there was, in this data set, there is a secular trend towards progressively more oxidized conditions in the mantle by about half a log unit, 0.5 to 1 log unit. So this would have been within the noise of the prior data. And Willie isn't the only one to have found stuff like this. There's another paper from 2016, Albach and Stagno, looking at vanadium-scandium ratios, now in basalts, not in Komatiites, make the same kind of claim for secular evolution. The scale is a little bit different. There's some argument about how to calibrate these two, vanadium partitioning versus vanadium-scandium, basalts versus Komatiites. There's some things to sort out. But at least two lines of evidence are arguing for some secular evolution, which they, in this paper in geology, explicitly linked to the great oxidation event. They tried to make that case. So we've done a little bit of modeling working with, this is really led by David Catling at University of Washington and his postdoc. You can take that sink term and turn it into these three sinks. You can do a little rearranging and focus on the ratio of the sources of oxygen to these sinks due to volcanic and metamorphic gases. So these are geologically speaking, the rapid sinks, right? Oxygen reacts pretty quickly with volcanic and metamorphic gases. Weathering is much slower, and so it has to be handled differently. And we can define this parameter K-oxy, which is the ratio of oxygen production versus oxygen loss, right? So essentially, if you are, K-oxy is positive, is greater than 1, rather. If K-oxy is greater than 1, then you have net oxidation. If K-oxy is less than 1, then the sinks are winning. So you can take the data I just showed you, feed them into a fairly simple model, and try to ask yourself, how would K-oxy have changed over time? When would we have, if you take that secular mantle evolution trend, and you can draw the line through here or through here, it doesn't actually change this all that much, as it turns out. Here's time 4 billion years ago. Here's the present. Here's this K-oxy parameter. Here's uncertainty in that K-oxy parameter based on the uncertainties in these fits. And what you find is that K-oxy flips from less than 1 to greater than 1 at around 2.5 to 2.3, 2.2 billion years ago. It falls out of the modeling without any special tuning. David was kind of shocked that the point of the study was not to prove anything, but to see, is it plausible that the secular variation that we see can explain the great oxidation event. We still can't prove anything, it's just a model. But he was kind of shocked that no special tuning was needed to demonstrate plausibility. It was the simplest case that fell out of the model. So again, this doesn't prove anything, but I hope it convinces you that there is a plausible story emerging, that there was secular evolution in mantle redox, and that that could explain the great oxidation event. We can talk a little bit later about why there might have been secular evolution of mantle redox. It's not clear, but there's some ideas. So the bigger picture, step back from that detail, is so surface-interior interactions are critical, which kind of makes sense when you think about it, right? The bulk Earth is an infinite sink for oxygen. Just pause and say that again. The bulk Earth is an infinite sink for oxygen. The interior is intensely reduced. So if you don't know anything else, we just approach this like a physicist as a fresh problem, asking in the abstract, without knowing any geology or anything, what would control oxygen at the Earth's surface? Sure, biology is going to be important because that's what's producing the oxygen at the Earth's surface. But surely interactions with the bulk planet's interior are going to matter, right? The rate of interaction, the mode of interaction, the chemical state of this is going to matter. And surely we should take seriously the possibility that all that evolves with time, right? That should be the zeroth order thing we should be thinking about. It's kind of odd that it's taken us a long time to really start to think about that seriously. And what that means is that to think about oxygen in Earth's history, deep Earth geoscientists and surface Earth geoscientists need to be working pretty closely together. Most deep Earth geoscientists have not thought about this oxygen question at all. Our FESD project was all about exposing at least some nice subset of interested deep Earth geoscientists to this question and attacking it in new ways. That's led to what I've shown you so far. But there's a heck of a lot more to be done because all sorts of questions emerge, like what caused secular mantle redox evolution and so on, which need geodynamicists and mineral physicists and others to address properly. So we need to drive this kind of integration between surface and deep folks, which doesn't happen naturally. You know, I found that I also led our astrobiology team for a while at ASU for 5 years. It's easier to drive conversations between biologists and astronomers than it is to drive conversations between deep and surface Earth geoscientists. And I have a theory as to why this is. The biologist doesn't expect that they know any astronomy, and the astronomer doesn't expect that they know any biology. So I literally have had the experience of having conversations in the room where the biologist asks the astronomer, so is phosphorus made in stars? And the astronomer asks the biologist, is phosphorus important biologically? And nobody's embarrassed. People laugh, but nobody's deeply embarrassed by their ignorance about other fields. But you put surface and deep Earth geoscientists together who are in the same departments, who went through the same curriculum, who should know each other's stuff and actually don't understand each other, and it's like nobody really wants to expose their ignorance to their close colleagues who they, I think that's just sociology of this thing is huge. So we need to do that. But now let's ask, what are the implications for astrobiology? And this will be brief. I know I'm running a little long. So what are the implications for astrobiology? If you realize that this is the challenge, right? It's this surface-deep interaction that shapes the story of Earth's redox history, I would argue. I haven't proven it, but I think I've made a good case that we've got to think about it. So let's think about the implications for astrobiology. Let's zoom back to our big picture. So here's Earth. Here is some Earth-like planet, right? It's a little bit bigger, maybe a slightly different chemical composition, but we say it's Earth-like, right? We want to point LUVOIR at it and look for oxygen in its atmosphere. Well, what are the consequences for partial pressure of oxygen and the history it might have had on that planet if that planet is a different mass than Earth? If it's 5% more massive, let's say. This guy's obviously more than 5% more massive. But let's say it's only 5% more massive. So I go to my geophysicists and geodynamicists friends and I say, okay, so let's imagine a planet that's just like Earth but is 5% more massive. How does plate tectonics work? And how would that ramify for oxygen history? And the answer you get is, we don't understand plate tectonics actually a priori well enough to give you more than an informed guess right now. Because, and I'm not slamming geophysics. I'm saying there's a huge reason to get better traction on the question of plate tectonics and how it relates to geodynamics that has nothing to do with what geophysicists normally think about, but it has to do with this exoplanet challenge. And both the geophysicists and folks at NASA ought to be talking a lot more. That's part of what the Nexus project is supposed to do. But this is not a trivial thing. How about different redox budget? What if the iron to carbon ratio is 10% different than Earth's? Or iron to oxygen ratio? So this is an idea that I actually learned from Dante Loretta, because years ago he had a student, Jade Bond, who started thinking about this and came up to give a talk at ASU, and it got me infected with this. Wow, this is like a big deal. Because we know that things like iron to carbon and iron to oxygen ratios are different among different stars, nominally sun-like stars. So how does that ramify to the composition of the planet? How would that ramify to the O2 history of a planet that has life just like Earth's? We don't know. We don't know enough to answer that question. How about different magnesium-silicon ratios, so that the viscosity of the mantle is a bit different, so the dynamics change? We can run fun models to look at how the interior changes, but it turns out the plate tectonics, again, is all parameterized at the top. So how that actually would affect volcanism and all this is a lot of hand-waving. So again, we can't really make the good predictions. Different volatile budget. What if the water content of the planet is a little different? What does that do to volcanism and degassing and all this? So what I would assert to you is that there is a systems science of the Earth that we are so ignorant of still, despite everything we've learned. And I'm not slamming anybody. We've done great science. We know a lot more about the Earth than we did, a generation ago, let alone 100 years ago. But a lot of it is still very descriptive and highly particular to our particular case with a lot of parameterization. We don't have a general working theory of how this thing works that allows us to make predictions about how that thing would work in some very basic ways that are going to be important to making interpretations of what we see out there. Especially to ruling out, what we'd like to do is a priori rule out false negatives. We'd like to know, is this guy worth spending a year's worth of observing time or whatever it's going to take, right, to be able to get an oxygen detection? Is it worth it? Or is this one that, because of its iron-oxygen ratio, magnesium-silicon ratio, one where that we infer from the stellar composition and some modeling about solar system formation processes, can we make a case that, well, that one's probably not a good bet. We probably shouldn't waste our time on that one. Oh, but this one is like really a good bet, right? We want that kind of knowledge, and we don't have it. So, and that requires yet another level of integration then. So we talked about deep Earth scientists and surface Earth geoscientists. Well, they also actually need to be talking back and forth with astronomers and other space scientists, right? So this is the integration that the NASA Nexus program is trying to drive. And this is what really needs to happen, right? And to the Earth scientists in the room, I would say that if you start thinking about this, you realize that this is is really cool because it would force us geoscientists to develop a much more general and generalizable theory of how the planet works. Because until you have that sort of a priori or semi-a priori understanding of how the solid planet works, you're not going to be able to make the kind of predictions that we're going to really need to search and interpret intelligently. And so it's kind of new frontiers for geoscientists when you think about it this way. But as a system, right? It's not like I'm doing this piece of this pale blue dot and I'm doing that piece. You've got to understand that whole system in an integrated way, and we aren't there. We aren't even, and we don't even in our geoscience departments, we don't talk to each other that way. And so, here, I'll leave it with this fun slide. So, once upon a time, James Hutton, one of the founders of the field, wrote a book, Theory of the Earth. When I was a grad student, Don Anderson, who was a professor at Caltech, had the temerity to write the new Theory of the Earth. Those of you who know Don know. What's that? So modest, right? Which really wasn't a theory of the Earth, but it was a nice explanation of what we see now. It was a lot of very good just so stories. What we really need is a true theory that's generalizable, that it would be a theory of Earths. And this is not something that one person is going to write. This is going to be a collective community effort somehow. And that's what we should be thinking about going forward. That's needed, and that'll be powerful for geoscientists. It'll be tremendously impactful in the search for life on other worlds. And I will stop there. Thank you. $50 minutes, not too bad.
I don't know if this is working. Oh, who has a hard question?
Yeah, if it's a hard
Or an
question,
easy
you can't
question.
ask it. But I'll take easy ones. No. Renu has one.
Great talk. I have a question about we discussed also about the stochasticity of the formation of planets.
Right.
And the environment around a star, and magnesium to silicon ratio of the star is important, but you can have totally different outcomes given.
So I glossed over this. There's how the planet works once you know its composition and mass and all that stuff. How does that evolve over time? But then there's how do you infer from a stellar composition, which is data we have and are getting better all the time, to a planet composition. And so that's a huge modeling issue, some of which is deterministic and some of which is stochastic because of random impacts and stuff like that. And so, yeah, so how important is the stochasticity? What kind of statistical description can we place on that as we improve our knowledge so that we could at least say, well, here's the likelihood that this kind of event would happen, likelihood that this kind of event would happen, and here's how it matters. So we're still too ignorant to, I think, have the informed conversation yet. But I think it's exactly right. It might turn out that random events are so important that all bets are off. I doubt that'll be the case. I bet we could put some kind of statistical limits on it, but that's a huge and important question. It's also, when you ask what causes secular change in mantle redox evolution, well, so one of the ideas is that there was early heterogeneity in the mantle redox that took a few billion years or so to mix in, right? So where does that initial heterogeneity come from, or what affects that? Well, those early events are going to play a huge role in shaping the heterogeneity or homogeneity of the mantle when you kind of start it on a kind of normal geodynamic evolution. So even forgetting about, so one aspect is how does the stellar composition translate to the planet composition? And stochastic events matter there. But then even if you understand that, we're also going to have to understand to what extent do late big impacts affect the heterogeneity of the mantle, right, before things kind of calm down. And we don't know the answer to that. It's a systems origin. So there's a systems question, then there's the systems origin question, right, which is also a kind of a systems challenge. It's a good question. Of course, we talked about this at lunch, so he knew exactly where the weak spot was.
Okay, this is really interesting. The thing that comes to my mind is this 2.5 billion year time mark that you say falls more or less naturally with a very simple model of the secular evolution of the redox state. The other coincidence, perhaps, that comes to my mind is the faint early sun. If you trace the solar insolation back in time, 2.5 billion years ago, is just about where we get sufficient solar insolation to have an average global temperature to have liquid water oceans.
With a CO2 only greenhouse. So it's what I've seen.
That's
yeah,
right.
So I've always been.
Is there? Yeah. So what are your thoughts?
I've always been struck by that. Back in like 2003, I actually wrote an abstract to AGU about that. Isn't it interesting? And could there be a story there? Could it be that, so we talked about this a little bit earlier, right? So this question about methane greenhouse, the importance of methane in the greenhouse effect, right? So could it be that before 2.5 billion years ago, 2.3 billion years ago, you needed methane to keep the planet warm, and that there are feedbacks that then, and methane and oxygen are antagonistic, right? You can't have a heavily oxygenated atmosphere and still have methane, right? So is it possible, and this is a very Gaian kind of thing to say, it's a very Jim Lovelock kind of thing to be thinking about, but it's maybe there's something to it. Could there be feedbacks in the system that, such that as long as you still need a methane greenhouse, oxygen stays low. And then once you no longer need methane to keep liquid water at the surface, then that feedback breaks down and oxygen can start taking off. So I've wondered that for a long time. I've never been able to I've never given it the time to put together a serious model. I've since become convinced that it can't be that the solid planet doesn't matter. It has to matter. So I've gone down this path. And I've relegated that to, isn't that curious? But it would be interesting to scratch the surface of that a little bit more and see how strong a story can be built. It's a really interesting coincidence. You can see it in Jim Casting's old papers, where he did these early climate models. And yeah, at about 2.5, you cross over.
Here you go.
Hey.
So for a theory of Earths, we need more than one Earth-like planet to study in detail, don't we? And so we have one right next door, Venus. It almost seemed to me like you just made the best astrobiological argument for studying Venus I've ever heard.
Well, I think there is a little subculture. I'm not the only one. I mean, there's other people out there who think strongly that we really ought to understand the divergent paths of Earth and Venus, that is like fundamental astrobiology. Here you have basically twin planets that went very different, and not just in their ocean situation, but the solid planet seems quite different, right? So what is that story? And there is this simple story we like to tell about, well, it lost its oceans, and that changed the tectonics, and catastrophic overturn. That's a nice story. I don't know if it really stands up to close inspection, and even if we think it is a nice story that should, well, let's go inspect it closer and see, right? So I think there's a ton of good arguments for a serious, attack is the wrong word, a serious investigation or campaign around Venus. It's kind of time. Nothing against Mars. I love Mars. Mars is great. But let's expand our terrestrial planet horizon.
So your previous slide, you were mentioning all the different fields that might be involved in this. And you mentioned other space scientists. Well, my field is heliophysics.
Mm-hmm.
I don't know if you know heliophysics well. And I was sitting there trying to think
I like the sun. The sun's
how
good.
the sun and space weather might affect this problem. Has that issue ever come up? Does it, besides the insulation problem, Ray knew about?
I'm sure there's things I don't know. My exposure to the role of the sun and all this has been around the solar insolation and evolution of the sun's luminosity, right?
Radiation events or something?
And I'm sure there are ideas out there that I'm just ignorant of. Yep. But when I said other space scientists, I actually was thinking in the back of my mind Venus and other solar system investigations. I mean, comparing Earth and Mars also is kind of instructive for some of this, right? We should be able to understand the differences between these planets, from a solid Earth standpoint, solid planet standpoint. We don't.
Great talk, thank you. So you had this great oxidation event, and then the oxygen partial pressure went down again. Do you have any idea why?
This overshoot?
Yeah.
Yeah, so it's a newish idea. It's only emerged like in the last 10 years, based on some lines of evidence that oxygen could have been quite high. The explanations for that I've seen are not all that strong or well thought out. It's a bit more of an empirical thing, and it makes some kind of intuitive sense that, the system changes and it kind of overshoots and then settles into some new equilibrium, right? But exactly mechanistically what went on, there's a lot of, for what I've seen, it's a bit hand-wavy still. So, and the evidence of the overshoot is not that strong, but it's interesting.
Anyone else? If not, I have a question. So
Uh-oh.
you kind of make it sound like it's a very precarious system and it barely worked, but
What?
the fact that we started accumulating oxygen, like it was very dependent on the mantle redox change.
Right.
So when you look at the model, if you start, looking at the sensitivity of the model to those, the rates of volcanism and metamorphism, how much does it change if you start playing around with those parameters in a realistic way?
I think it's a really good question. I think so. I'm going to kind of insult the modeling community who does ancient atmospheric modeling. There is this, what has been done for the most part until now is to basically say, well, we have modern rates of volcanism, let's just extrapolate them back because we don't really have any good reason to do anything else, right? And let's just take the modern and use that as but we know the solid planet, we know tectonics are different, we know that all this was different, but we don't know how well enough to feed into the models. And so the modelers, like Dave Catlin would probably say to you, yeah, that's a good question, tell me how I should vary it. That would be plausible. Not you, but the solid Earth folks. And those conversations haven't happened enough yet. But yeah, I agree with you. That's the kind of thing that ought to be done. You saw the error bar. You saw that there's actually a confidence interval on that curve. So that's already like more sophisticated than most modeling I've seen. Of trying to at least take of this type.
Okay, well, if there are no more, let's thank Ariel one more time.
Thank you guys.